talk about that in vision, vision transformer is very important. So you really need to understand fully. And it's called also VIT. And this was the first paper in 2021. Already have 50,000 citations, about 4 years. So as we talk about the whole thing in the NLP is the tokens, and tokens are the words, and these are meaningful words, they're semantics, that's language, the way it works. But now the image is the pixels, these are the numbers, right? So that's why computer vision is more challenging than NLP, because we have to start with the image, numbers, and convert them symbols like objects and segments and labels and so on. So now if you look at the image, and other problem with the image is that it's a high resolution. There are lots of data, right? So then, if you look at, ideally, one pixel can be a token, but there are lots of tokens. So we won't be able to deal with that. So therefore, image is divided into 16 by 16 pages, and each of the pages is a token, like a word. It's a visual word, you can say. And transformers are trained on the large data sets. So this particular method trained on this 300 million images, which is called JFT data set, and that was 4 years ago. Now, we have billions of images also, and receive very good results. So, on the ImageNet 88.5, ImageNet Real, and CFAR, and all those other things, because that was the first, demonstration that transformer works for the vision, because transformer was very successful for the language. So it looks like this, and it's mostly encoder. So we take an image, divide in 16 by 16 these pages, do the linear projection, and flatten the 16 by 16, which would be 256 by 3, because the RGB, and then we have position encoding, then go to transformer encoder, different self-attention, MLP, and so on, and then you have output here, and that will be used for classification. You can do image classification, okay? So, and this is the standard form of transformer, the normalization, multi-attention, skip connection, normalization, MLP. Okay, we have talked about this. So when you divide an image, say 224 by 224, so we will have 14 by 14 tokens, okay? So that will be 196 tokens for this image. And each page is 16 by 16 by 3, so it will be a 768 dimension vector for each of those. So it looks like this. And so these are for each of the token, total 196 tokens or pages. Each token is represented by 760 dimensional vector, okay? And that's called page embedding. Then we will have one token, which is called CLS token, classification token. So we will have then 197 tokens. So then complete VIT looks like this. Page embedding, 768 dimensional vector, and then the position encoding, as we talk about, that also same dimension, and then goes encoder, and after that we get the classification, okay? So they look at the different versions of these VIT. Base has only 12 layers, VIT large has 24 layers, and VIT huge has 32 layers. So that was one thing you will notice when you come up with the LLM or VLM. They talk about 7 billion parameters, 70 billion parameters, so on. So only difference in these structure is same, just keep adding more layers. More layers means more parameters, and you can learn more. But in order to learn those, then you have to have a lot of data. So as you see here, the simple base is 86 million parameters, but the huge has 632 million parameters. Okay, so then then each token dimension 768, the simple one, but you can increase to 1024 or 1280 and all these things. Then each of the layer, then we have heads, as we talk about multi-heads self-attention. So that's the way it works. So they show that this works pretty well. Different versions, huge, large, and all those things. And this is the page size, 14 by 14, 16 by 16, and so on. And they compare with the image, the other method, resonate and EfficientNet, on all these metrics, and they found out it works pretty well. So bold means higher. Okay, so so that is about the VIT. Now there was a paper called Swin, as I told you, that got a Mar Prize in ICCV, and Swin improved further on this. And so again, they wanted to address this issue of the self-attention, because as we talk about, the complexity of self-attention is order n square. Depending on how many tokens you have to compute these cross, the cosine similarity for each token with all other tokens. It's a matrix. So if you have this so many 196 tokens, so you have 196 by 196 matrix, and for each one you have to compute the cosine similarity, which is 768 dimensional, dot product for each of this. A lot of computation. So that is the the issue to solve it. And these guys give the motivation why they want to do that. So they came up with this Swin transformer, and it does not compute the attention for the whole image, but it's a local window attention. And these windows are shifted. That's what the name is, Swin, shifted window. Okay, so shifted window limits attention, the computation is faster. The local windows, and then allowing windows across the connections. So standard VIT is all the layers, we have 16 by 16, okay, it's fixed. So here, Swin, we start with a small window, actually 4 by 4. Then we go to 8 by 8, and 16 by 16. So it's like a scale, we are increasing. So then they demonstrated that this can do pretty well. These are whenever you publish a paper in Vision, so you have to have a novel idea. Then novel idea has to work, which means you have to show the performance of your method compared to on all these benchmark compared to other methods. If you are able to show that it works better and also it is new, then you get paper accepted. Otherwise, paper won't be accepted. Okay, so that's important. That's what we will see these numbers. So now one good thing about the Swin was that they show not only classification, because simplest thing you can do in computer vision is classify images. Given an image, you say what class it is. But there are more interesting, more difficult problems. Dense prediction. For example, detecting object. I put a window bounding box in the image, say, well, this is the airplane. But you don't only say that in this image there's airplane, but you don't know where it is. Okay? So that's why for this matrix different, it is called average precision. And the data set is different, it's COCO data set. So it's semantic segmentation, where you want to classify each pixel. This pixel is the building, cloud, or the road, or whatever that is. Okay, so there's another data set called ADE20K, and there you want to look at the intersection or union. You have a ground truth, and you have the detected. You want to say how close the detection mask is with respect to what the ground truth. So they got these state-of-art performance on these also, okay, on these data set, COCO 88 tunica, and so on. So the architecture is again very intuitive. So you start with an image, is the height and width and 3 channels RGB. So you do the page partitioning, and each page will be 4 by 4. So therefore you divide H by 4 and W by 4, multiply, you will have those many pages for the image, which is H by W. And since it's 4 by 4, so it'll be 16 pixel, and RGB, so it'll be 48 dimensional vector, as compared to 16 by 16, where we have a 768 dimensional vector. Okay? So then you go to the stage 1, and you do the linear embedding, and you have these Swin transformer block, two of those. And these blocks basically are the self-attention and all those standard transformer blocks. So then we go to next thing. Now here we are going to change the dimension from 48 to C, and they have different values of C, 96, 128, 192. So now you can take any size of a page. You don't have to limit to the size of the encoding of the token to same one. You can increase or you can decrease, it's fine. You can put another layer and go to that one. So now for the stage 2, what will happen, that we are going to merge the pages. Remember I told you 4 by 4, then 8 by 8, 16 by 16, and so on. So that way, then out of this, for stage 2, now we will have these many tokens. It will be fewer tokens, okay? Because we are dividing H by 8 and W by 8, but each of the token will have a higher dimensional representation, twice C, 2C, as compared to C there. So we'll do that, and then we have a stage 3. Then again we'll merge the pages, and then now we will be divided by 16. So that'll be 16 by 16 page, and then we'll increase the dimension of the token to 4C. Okay, so we'll have 6 blocks of those, and then we'll have a stage 4. Then again we will increase to 32 by 32. So that's the scale space. That's what we are doing, and that's their main contribution, and it works. And what this is doing, that it's reducing the computation for attention. You don't have to do for the whole image. So that's it. So now these the Swin transform blocks are like this. So we have input, linear layer, window, multi-self attention, and then skip connection, linear layer, MLP. Then after that, it goes here, linear layer, this is shifted windows, multi-edge self-attention, and then skip connection, linear layer, and so on. So we'll go in detail this thing, okay? So layer 1 is like this, and then layer 2, when we shift it, we'll shift halfway. So here, as you see, that we are taking half of this window and half of the next window, and that's kind of capturing the relationship of this, and we keep doing that, and that's why we're going to capture the whole image. Okay, so now the transform block is here. So what we're going to do is we start with the ZL minus 1, which is the L, this coming from the L minus 1th layer, go the linear, and then window, multi-edge self-attention. Then we will add the self in the skip connection, ZL minus 1. Then after that, then we will take this ZL head and again linear layer, which is coming here. Then we will do MLP, and then we will get a ZL. Okay, so this way we will get a ZL from here. So again, let me explain this again. I kind of missed it a little bit. So we come here, ZL minus 1, then linear, and the window self-attention, then skip connection, so ZL head, which is shown here. Then we take a ZL head, linear, MLP, and then add this again the skip connection, ZL head, and we get ZL, okay? It's from layer L. So that now goes to here, the second block, and for that, we will take the ZL linear layer, and this is now shifted window self-attention, which is here, which is different, shifted, okay? So then we will do the skip connection at the ZL, and we'll take that one, then we do linear layer here, and then MLP, and then we do the skip connection here. So it's very simple, nice, we just continue. So main thing is that we have to shift, and it's a local, okay? So that's it. So again, here they have the tiny, small, base and large, and they have different dimension of the token size, 96, 128, 192, and number of layers. Remember, there were 4 blocks. So in the first one, we'll have 2 layers, 6 layers at 2, but they vary and they have some different results for that. Okay, so here are the results on the ImageNet 1K, and they can compare with the VIT, DIET, and other one, and they do pretty good. And these are the performance ImageNet, and this is size of an image and number of parameters and flops and all those things. So this is on the other data set, ImageNet 22K. Again, they show they do pretty well compared to VIT, and performance is good. I mean, here even 1% is a big thing, which is good. This is on the mask CNN, which is object detection. Again, when you see the bold one, which means higher. So this is 50, and this one is 46, resonate, diet, and so on. Okay? And this one is another data set of AD E20K, and the same idea here. So in summary, VIT is the first vision transformer trained on a huge data set of 300 million images. Swin is a next version of that, which implies a window attention, and that's the performs well on other tasks compared to the VIT, object detection, semantic segmentation, and so on. Okay, so that's the end of the lecture 3. So I'll stop here and give you a chance if you ask any question about the transformer. Who has question? No question. Yes.
I have a question about why Swin is needed. So self-attention only happens within the patch, or is there attention in between the patches? So and is there a different scheme that you can use to transfer the self-attention besides Swin, such as making a smaller patch or creating self-attention between convolutions?
There's no convolution here. You missed the first class, right? You were not here Monday. So self-attention happened with all the pages, all the tokens, right? So and self-attention, the idea is that you take the token embedding and find the cosine similarity. So we talk about the here simple example. I went through here, so let me explain here. So so this one is let's say we have 4 words: hi, how are you? And we have embedding for hi, which is here, for how, which is here, and so on. So it's a vector, okay? So attention means that you want to find out how much support this representation get from itself, from this one, and this one. And we will get this line, this row. Similarly, we will find out the attention for this one it gets from itself, which is this one, and from this one, this one, this one will be second row, and like that. So that works like the cross product, that dot product. So suppose this is representation of the first token, representation of second token. To get this entry, we will find the dot product like that. So self-attention is between a token with all other tokens. So in this one we have 4, so we'll have 4 by 4 matrix. We'll have 16 self-attentions we have to compute. Okay? So you can review that. If you have more questions, you can ask later. Okay, from the Zoom, are there any questions? Please unmute and start talking.
Yes, Professor.
Yes.
How do the VIT and Swin scale with increasing dataset sizes?
How the VIT
And Swin perform with scale for increasing dataset? Which one is better?
scale the data set. See the when you say scale data set, which means the number of sample of
Like when increasing the dataset, which one perform better?
Yeah. So when you say increase data set, which means that you are increasing the number of samples, right? So you have more images. Yes. Now
Yes.
each image, as we talk about, the complexity is order n square, which means each image, if they have n tokens, then we will have n square computation. As I just explained here, we have 4 tokens, then we will have 16 computation for the self-attention. So if you increase the data side, there will be more computation. Now as we show that the Swin does not do for all the tokens, the window. So in this case, we can say we will do attention by 2 by 2 window, not all the 4. So therefore, Swin always will perform better in computation as compared to the VIT. Okay?
Yes, thank you.
Okay, any other question from here before we go to clip? Okay, so let's now talk about clip. So this one. So this is downloaded, right? Okay. Okay, so clip contrastive language image pre-training, and this was a paper in ICML 2021. It has 27,000 citations, and this is the paper I think we discussed in 2023. So this presentation is from the group they presented, so I made some improved slides. So we'll go through again, we have a YouTube video. It has a lot of hits actually, this particular video. So that's for short. It's called CLIP, Contrastive Language Image Pre-Training. I is for the image, and P is for pre-training, and L is for the language, and C is for contrastive. Okay? So again, the big thing has happened, starting with CLIP, that we are bringing in the language in solving computer vision problem. And the language, because it's good for humans, we communicate with language. So the images, and when we analyze images, we have to communicate which class object it is and so on. So the language helps. Okay, so the main point is that we have an image and we have a corresponding caption. And there are lots of images on the internet. People upload images and they have also captioned to describe what the image is, and that's what we want to leverage. Okay? And the good thing is that when you bring in this, then it beats the other approaches where we are using only image information, not the language. Okay, so also good thing is that we can do zero-shot classifier, and I'm going to explain what we mean by zero-shot. Okay, so the simple way to explain this is that we have an anchor, we have a sample, and then we have a positive sample, which means similar. And we have another one which is negative, which is dissimilar. So learning idea here is that we want to learn, so that at the end, the idea is that we want to learn the representation of image. We want to come up with feature vector of image. We want to learn such that the positive pair, the representation of this and representation of this should be similar, close. And representation of this and this should be far away. So that it is separate. So this is space, suppose a 2D space. So these two are similar, they are closer. And this is different, it's far away. So that's the idea. And we want to put these in the same semantic space. Here's an example. So we have input image. It's an image of a dog. And we have a caption which says dog lying in grass. So we want to learn the representation of the image. We will call HI, a feature vector. And we also want to learn the representation of the text, which we'll call HT. Such that since this image and the caption is correct, it's a positive pair, okay? So we want to maximize the similarity between two representations. And similarity of two vectors is a dot product, yes? And we normalize it with the magnitude of that so that it's a scale. So that is our criteria. Whenever you want to learn, you have to have objective function. You have to have criteria how you want to learn. And it's pretty intuitive. Okay, so now look at negative pair. So we have an image of an airplane, but the caption is same, dog lying in grass. It's a negative pair. So we want to take these two representation, we want to minimize the similarity between these two, we want to minimize. Again, the dot product, but we want to minimize. So that's the idea, okay? So that's called contrasted learning, and you will hear this a lot of time. So now what we are going to do, we will have a bunch of pairs, text and image, and we are going to learn this, okay? So we will learn the text encoder. So we have, say, n image and text pair. So we'll have T1 will be text encoding of first, T2 will be second, third, and so on. And then we will have similarly the image encoder, image embedding of first image, second image, and so on. Okay? So, and then we will find the dot product of these two for all these. Okay? So I1 with T1, I1 with T2, and so on. So it will be a matrix. So encode batch of text sample, encode batch of image samples, maximize the cosine similarity between correct matches. So we have here, same thing. So we are going to represent MI, it will be a one hot encoded label vector for ith image. One hot encoded label vector is a vector where only one element is non-zero, remaining one are zero. So that which is one is hot, remaining are the cold. Okay? So that is the MI. So let's say the I3. So we'll have vector which will be, 0, 0, 1, all 0. 100 encode of third. Okay, so then we will have cosine similarity vector of the ith sample. So we will, because we are computing the cosine similarity of that image with all other texts, so we will have this vector, and which is shown here. Okay, so we have the cosine similarity of I3 with I1, with T1, I3 with T2, I3 with T3, and so on. So this is a vector. These are the numbers, yes? And there's also a distribution. So now then we will have Ti, which will be one hard encoded label of the I text sample. Same thing as we did for the image, we'll do for the text. So, which is like, let's say T3. So then we will have again cosine similarity of vector for the ith text sample. We'll have this column. So first was rows, second was column. So then we'll find out the cross entropy loss. Okay, so these are distributions, right? That's 100 encoded as a distribution. It's just 100 encoded. This cosine similarity distribution. So it numbers from 0 to 1 probability. So now, if you want to find out the similarity of two probability distribution, you look at the cross entropy. That's what you train your classifier always. So therefore, so this cross entropy will be expressed like this. So we have two distribution, P and Q, and entropy is given by the Pi log Qi and for all the bins. So that's it. So then this was for we take an image and find with all these samples, the text, and that's what we are doing here. As you see that this will give us this one row, and we are going to do that for all of these samples. Okay, so this is for only mth vector, which is say this one. So this is, we are matching image with the text, all the possible text. We'll have similarly for the text, we'll match with all the images. So which will be like this, a column. And that will be like this. So now here we are going to do the Ti and with different I values here. So that will be the similarity of text, image, and we'll add up these two. And this will be our loss function, and we are going to train this. And training means that we are going to find representation of the text, representation of image, and that's it. That's what CLIP does. Okay. So now, if you look at what you learned in the 5415, that most of the time you do supervised classification. So like this is the CNN kind of thing. You take an image and you go through different layers, and then at the end you want to come up with the distribution. If you have 10 classes, you'll get 10 dimensional distribution and say which particular digit this is. So in order to do supervised classification, you have to have labels. You have an image, and you know the ground truth, and you will put an image, and this neural network predicts something, garbage. Then you compare that with the ground truth and look at the loss. And this comparison is done cross entropy. Okay, that loss you want to minimize. You want to make them similar distribution. And you keep doing that, then it will learn. So this was about the supervised classification. We know the labels. We know the ground truth. Okay. So the good thing about CLIP is that we can do this without labels. We can do what's called zero-shot classification or learning, which means we can classify images for which we haven't trained the network. Okay, and this power of the language. So if you compare with supervised learning with the zero-shot, then supervised learning we need label data, zero shot, we don't need it. We don't have to have label or unlabel. We can do without label. So there's a training, phase in supervised learning, but there's no training. We don't have to do training. Okay? Zero shot means we need zero labels. We need zero shot, zero sample to do this. That's what it comes from. So final prediction we can do on label data, but here we can do accuracy and final results. And so let's look at here the problem, kind of we want to do zero shot because whatever we train the neural network, it's a limited number of labels, right? We have a classifier for 100 classes. Then if you have 101 class, we have to train again. So that's a problem. So it will generalize. And in a way, CLIP overcomes these limitations. Okay? So again, zero shot, we train on one data set, then generalize on unseen categories. And I'm going to show you example. Okay? So here's example. So let's say we have trained on these classes like dogs and boat and horses. So we can take these images to test. Then we can recognize these things. But now these are the unseen classes. We haven't trained for donkey. We haven't trained for jet ski. And it can do that because we have learned this same semantic space. Okay? So how can we do that? So what we are going to do, because remember we have learned these encoders, the text encoder and the image encoder. So suppose we want to recognize this particular class, say donkey. Okay? So what we are going to do, take the donkey here and we will generate our own synthetic sentence, a photo of a donkey. Okay? Then we'll put in text encoder. And then we have an image. We want to classify that. We'll put an image encoder. We will get its representation. Now, there can be lots of classes, right? So we'll just compare that this image embedding is, which is the closest one to this class. And that's a class, even though we haven't trained for that class. So that's the idea, because we are putting in the same semantic space. So, so they're used for web images, and they actually came up with 500,000 text queries, how they generated this data set. And this data set had 400 million images and about 20,000 pairs per query. So the architecture is simple. So you have byte pair encoding for the text, your transformer encoder, 12 layers, 512 with 8 heads, and you get this representation, linear projection, and you get text feature representation, and very similar to for the image, and you get the image features, and then that's it. So the training was done on these 400 million images, pairs, and this was a very large batch size, 32,000, these many epochs, and so on. They did this on ResNet and also VIT, and transformer-based encoder. So testing. So here what we are doing, we are just learning the representation, the features of an image and features of the text. Now, once given that, then we can do other things, right? So suppose we want to do classifier, so we can get the features and return a classifier if you want to supervise, or you can do zero shot. So the classifier, they can do linear probe, like train a classifier, or you can do zero shot, as I explained to you. So train a classifier, you can just use clip features. So they did performance on this data set, corn, blith. These are 12 data sets, which are shown here. The food, CFAR 10, 100, birds, sun, Stanford cars, and Pascal, Oxford Pates, and so on. Caltech 101. So these are the number of classes. Each of data set, training size, test size, evaluation matrix. Then they actually extended this to 27 data set. So these were the original one, and these are the additional one. Okay, so these are the results for the first part. And as you see that they are comparing clip VIT with clip resonate. Clip VIT is the top. Okay, and then clip resonate is not doing that well for this one. But they are comparing with all efficient and other SimClear self-supply learning method and so on. And these are the how fast you can do. So on this data set, they got transformer-based method works pretty well. Clip resonate underperforms, and clip VIT outperforms. And this is on the extended data set of 27 data set. In this one, both of those, the transformer VIT and the resonate perform pretty well. So that is the score. So now let's look at zero shot. So as we explained earlier, this is the way zero shot works. So this is on zero shot, Stanford cars. They can actually do 28% more food and so on. It's pretty impressive. And this one, so this is actually compared to linear probe resonate, which is actually supervised, but they are comparing with zero shot, so they can do better with zero shot. And then they can actually do the UCF 101, right? So you should be happy to see UCF 101. This is our data set, and everybody uses. Okay, so then there were some data set they didn't do well. Suppose the bird snap and MNIST and so on. So it's a negative because they are very different. They are the yes.
UCF is a video data set.
Yeah, yeah.
So how did they like?
Yeah, so see they did for each video they just took this middle frame.
One frame.
Yeah, and they show on that one.
That frame can be like.
Yeah, so I mean the data set is simpler, so it works. But if you do more, like see them, I mean they at that time they were doing 7% better. But if you use video information, there's a whole thing about video clip also. You can do that. Okay, so these other data set where they don't do well, they are very different. They are satellite medical imaging, depth map, and so on. Okay, so other thing they showed that it is more robust. So here, simple ImageNet, they do same performance compared to ResNet. But now this is ImageNet V2, where they have a variation of, suppose, this banana class, different. And in that case, they are actually doing better than ResNet. And this is another one, ImageNet rendition. There are different kind of images. They actually do very well. This is the ObjectNet, another data set. Again, they do pretty well there. And this is just sketches, not images, and they do pretty well also there. And this is the adversarial attack, if you can do, and they also is robust to that. So now you learn the supervised, where you have the labels and you train the classifier. Then you learn the zero shot, where you don't have labels, no training, just do that. Then the next thing in between is low shot, that you have few labels, okay? Say it's up to 16. So if you have this learn clip model for image features, then you can fine tune on these label data. Few examples, it's called few shot, and they also show the comparison with this, that they can do better clip as compared to other Sinclair, HazeNet, and so on. Okay? So it scales very well, and it climbs, and all this thing. Zero shot clip out from all non-clip method until 16 shot. So then, now there are methods where you don't need supervision. These are called self-supervised method. Okay, so Sinclair is one of the method very popular, actually by Hinton. So here, the idea. Remember, the clip, it was a pair, an image and a text pair, and we were doing contrastive learning with that. So here is similar idea, but we have an image and augmented version of the image. Okay, but again they are the same. They should be similar, right? So here what we have done, that we have just changed the color, or we have cropped it. So that's called augmentation, and you do the augmentation, data augmentation, to generate more samples. And so you can do contrastive learning with that. Since this is this image, you do two augmentation, so these should be similar, attract, and this is a completely different object. Two augmentation, they should be attract, but these two should be repel. So the same idea, right? So the Sinclair self-supervised learning method. So this is purely image-based, no text here. There's another method, self-supervised method called MAE, mask autoencoder. You take an image, they are patches, they are tokens, you mask them, make them zero. Yes? You put an encoder, then decoder, then predict the mask tokens here. You learn to predict, and that is another way, and it works pretty well. So then we have the clip was a beginning, and then there are lots of other variation of clip, right? So as you see that what we have is the input image, input text, we have vision encoder, text encoder, and we learn this using the contrastive learning. Positive pair should be close, negative should be repel. There are different versions of them. We go through some of these. So Florence, flip, align, and so on. There's easy clip, and there's many other versions. Sig clip, and so on. Then we have another version of the clip idea. So here we use only contrastive laws. But in addition to that, we can apply the self-supervision laws, right? So we can mask some of the token and predict those. At the same time, we can do the contrastive learning with that. Or we can do augmentation and put the contrastive learning with that. So we'll have two losses, image, text, contrastive, and self-supervision. And there are several methods like that. And then another version where we can do this clip with image masking. This was just self-supervision, and that can be just in clear, but another self-supervision will be masking, and we can just do that, image text contrastive. This one is, we can actually mask our text also. We can mask